Intercrops, I would like to start with weeds. What are they? It would be nice if this would work, but then I have to turn it on. Well, if we look at agriculture and we are growing annual crops, then we're starting off with preparing the field. And that might be an inversion, plowing, it might be a seedbed preparation, and then sowing will occur. And after the sowing, the crop is meant to establish itself. And that's also what usually happens. But apart from that, also spontaneous vegetation appears. And those are the plants that we know as weeds. And well, if we are not doing anything about that and we just let them grow, then for sure those plants will take over and they will cause an enormous yield reduction. And that is what you can find over here. Cousins established the relation between the weed plant density and the yield loss one can expect. And depending on the competitiveness of the species, this slope will be high or it will be lower, but whatever happens, you'll get yield reduction. So farmers for sure will do something about it. Another question one can ask, okay, what kind of species do show up as weeds in an agricultural setting? And of course, we can imagine that those are the species that are very well adapted to edible farming, to an agricultural field. And if we look at the characteristics of an agricultural field, we can see that in the field, there's frequent disturbance. And the plowing, the seedbed preparation, the weeding, but also the harvest, all the time, the vegetation that has established will be removed. So there's an enormous amount of disturbance. At the same time, the farmer will take care of the crop, so it will also supply either water or nutrients if they are present in a limiting amount. And so the conditions of an edible field are typically a high level of disturbance and a low level of stress. And then everyone, of course, knows more or less where I'm going to, and specifically Gerlinde, one of her favorite ecologists, Grime, developed a nice scheme, the triangle, the CSR triangle, where we have competitive species, we have, depending on disturbance, we have ruderal species, and we have stress tolerating species. So depending on the circumstance, certain species will develop. And typically in conditions where you have a high level of disturbance and a low level of stress, ruderal species thrive. And they are typically favored by those conditions. And some of the characteristics that are typical for ruderal species are a high initial growth rate. And once they establish, they usually germinate on a bare field, so they quickly have to establish themselves. They usually have a very short vegetative period because soon the crop, after a couple of months, will be completed and will be harvested. And before that time, those plants should already have set seed. And also the seed phase for those species is very important. They survive in the soil as seeds, and they also usually have a dormancy mechanism so that they will not germinate all the time, but in a kind of batches to have a kind of risk avoidance. And some species germinate at a certain moment of time and others germinate at another moment of time. So those plants or those weeds are also called pioneers of secondary succession. And so for them, competition, of course, is important, but I would like to point at this issue. For them, it's very important to have a very fast early growth rate, because that for them is their reason of existence. So farmers take measures. A very important one is curative control. So weeds have established, they have developed into weed seedlings, and they take all kinds of measures to get rid of those plants. And actually what you are doing in that situation, and this is the Cousins equation again, well, if you wouldn't do anything, this would be the weed density. But if you remove those plants, you lower the weed plant density, and consequently also your yield loss will be reduced. So that is in fact the strategy that is applied when you apply curative weed control. Well, after curative weed control, because that is usually necessary to get rid of the very first emerging weeds, gradually the crop might take over. And because the crop develops, it gets taller, and it's better able to suppress those weeds that emerge or establish at a later moment of time. And to determine from which moment of time on you do not have to take curative control anymore, there's a nice experimental design. And let me try this. This is the start of the growing season. This is the harvest of the crop. And what you could do is you could have a treatment in which you control the weeds until this moment in time, and then don't control anymore. And then you can imagine that from here on, the weeds are able to establish, and the yield you find will be relatively low. So if you continue with control for a longer period of time and only switch to no longer control over here, the yield will already be higher. And at a certain moment of time, you can imagine, okay, now the crop is really in control and you don't have to take a curative control measure anymore. And that is what is referred to as the minimum weed-free period. So in this case, beyond this point, the crop is able to take care and you don't have to worry anymore as a farmer. Now you can imagine that the length of this minimum weed-free period for a crop which is very competitive will be relatively slow. And so already very early on, the crop can take care. But if you have a poorly competitive crop, like onions or carrots, then this minimum weed-free period will be way longer. And the farmer has to take care for a much longer period of time. So this is what you can modify, and also what farmers are doing. One of their strategies is to increase the competitive ability of the crop. Had to make sure that already early on the crop is relatively competitive, so that curative control is no longer needed anymore. And we can see various measures. Transplanting typically is an example where you give the crop a head start. You can increase the seeding rate. Over here, this is 100 seeds per meter square. Over here, 500 plants per meter square. So the crop is way more competitive. You can also decide on which cultivar to use, because there will be differences in competitiveness between the cultivars. And you could also think of putting the plants in the field in a more regular pattern. That will also result in a faster canopy closure. Yeah.
Question. In crop breeding, is these kind of competitiveness in the initial growth phase and taken into account?
Yeah, usually what you find, if you look for traits that represent competitiveness, it's found that early vigor is a very important one. And so those crops that really are growing very fast initially, they are usually the more competitive ones. So kind of resembling the weeds. Of course, height also has an influence, but that's more later on in the season. So usually in those experiments, you find early vigor to be the dominant trait for competitiveness. Okay, so what we are now doing, in fact, is we are lowering this angle. So the influence of the weeds on yield is reduced simply because we are giving the crop a better head start. And now, of course, what you can think of is, can intercropping perhaps play a role in this? So could an intercrop also result in a more competitive canopy? And that was also the idea behind the study of Daniel Baumann, who looked at leek and celery. And leek, of course, is a very open canopy, so lots of opportunities for weeds to develop, whereas celery is way more leafy and covering the soil relatively early on. So you could think of a combination of those two, where in fact the celery more or less protects the leek from the competition with weeds. And that is what he investigated. So here an alternating row pattern with a row of leek alternated with a row of celery. So one of the things he did, he measured light interception, and the upper graph, the green one, is the light interception of celery, the more leafy crop. This is the light interception of leek. And what he found for the intercrop, that's not something in between. Well, it is in between, but not exactly in the middle. And so you can see that the celery is way more dominant in the intercropping situation. And so also there you can expect a faster canopy closure. He also tested the concept of this minimum weed-free period by introducing weed seedlings in the crop at different moments in time. So he took seedlings of Senecio and he introduced them at 4, at 6, or at 8 weeks after crop establishment. And then he looked after a while how many of these seedlings managed to survive. And when you look at the situation in leek, the very open canopy, you can see that particularly early on, when it's 4 or 6 weeks after planting of the crop, many of those seedlings survive, and only at 8 weeks after sowing, more of them got killed. If you look at celery, the more leafy crop, quite a number still survived when they were introduced at 4 weeks after planting, but then already quite a number of them got killed or did not survive. And when you look at the leek celery intercrop, clearly there's an intermediate situation, but it more closely resembles what you observe over here than what you observe over there. So this is basically the concept, what he had in mind. If we have just a leek, a monoculture, we have a very long weed-free period. And so the period that a crop has to be kept free of weeds to avoid yield reduction. That means a lot of operations, and if you do that on an organic farm, you will need mechanical weeding, and then from there on, the crop will take over. But now if you introduce an intercrop, you considerably shorten the weed-free period, so you can do with fewer weedings, and from there on, this combination of leek and celery will take over. So in fact, the system has an advantage, which is reflected in a reduced weeding effort and also in a reduced yield loss. And so the intercrop clearly has advantages over this leek monoculture situation. Now, more recently, we had a PhD student, Chun-Feng Wu, and she made a meta-analysis, and I think you're also going to talk about meta-analysis in this course. And she made a meta-analysis on papers that mentioned the weed biomass that was observed in the pure stands, but also the weed biomass that was observed in the intercrop. And then she had a look at that. And something similar was already done in 1993 by a famous paper of Liebman and Dijk, who compared intercropping situations and crop rotation situations. So clearly a paper on crop diversification and the influence, the positive effect that might have in weed management. And surprisingly, they found more or less the same result. And so if you look at the weed biomass in intercrop, sometimes it's more than in those two crops, in pure stands of those two crops, which is something you would not expect, but okay, that is what was found. In about half of the situation, the weed biomass was in between the stronger competitive crop and the weaker competitive crop. Perhaps a situation which you might expect. Also, in quite a number of cases, also more or less 50%, the weed biomass found in the intercrop was lower than in both pure stands. So on average, you can clearly see that an intercropping situation, an intercrop, seems to have a positive effect on weed suppression. So then Gu, she took it further and she looked at, okay, but how now did the weed biomass in the intercrop relate to the weed biomass in the pure stand? And in this case, the pure stand of the poorest suppressing crop. And then of course you would expect that the weed biomass in intercrop is lower than the weed biomass you find in a poorly suppressive crop. And the question is, okay, how much lower? And that is what you can find here. On average, the weed biomass in the intercrop was about 58% lower than the weed biomass in the weakest suppressing crop. And she did the same by comparing the weed biomass in intercrop to the weed biomass to the stronger competitive species. And then, of course, you would expect that the weed biomass in intercrop is somewhat higher. But her results indicate that it's higher, but it's just a little bit higher. And so what you can clearly see from those data is that usually the weed biomass in intercrop is in between those two pure stands, but it's much more close to the weed biomass you find in the stronger suppressive species. So it does better than the average of the two. the average of the two pure stands. Okay, so something is going on in the intercrop, and therefore we would like to know what exactly is going on, because if we know what is the mechanism behind, that might also give us clues on how to design an intercrop so that the weed suppressive ability of that intercrop is at its maximum. And well, if you look at the mechanisms that might be at play, and I imagine that this terminology has been introduced already, complementarity and selection.
Quite.
No?
It has not been defined. We're sort of assuming that most people are familiar, but maybe you can explain shortly.
Okay, well, if complementarity is at play, that's a big disappointment, Jochen. 2 days of intercrop.
It's only half the course, not the meeting, so.
Complementarity simply means that the two crops partly make use of a different niche. And therefore you have niche differentiation. You have a more complete amount of resources that will be taken up if you combine the two crops. And as a result, fewer resources will be left for weeds. The second mechanism might be, of course, that the crop species that is most competitive takes a larger share of the intercrop and more or less also to some extent suppresses the weaker suppressing species. But as a consequence, the weed suppressive ability of the intercrop will be more than average. It will be closer to the weed suppression of the more suppressive crop. And that is what we call the selection effect. And then what was also observed is that in some situations, the plant density in the intercrop was higher than the plant density in the two pure stands. And if that is the case, we talk about an additive intercrop. And I'm sure that has been introduced.
Do crops ever show allelopathic?
Yeah, some crops do show allelopathy.
Which one?
It usually depends on the variety, but for instance, rye is known to produce quite a bit of allelopathic compounds. And then they also have a negative effect on the growth of other surrounding species like weeds. Yeah. So allelopathy is sometimes at play. To prove that it's allelopathy is usually quite a challenge to distinguish competition from allelopathy.
What is allelopathy?
Allelopathy is that the root system of a plant exudes certain compounds, and those compounds have a negative effect on the growth of other plants.
Any other?
Sorry?
Any other plant? So,
Yeah, well, the plants that are sensitive to that. And so that might also differ among plant species. But it's the excretion of compounds, usually through the roots, but it could also through the aerial compounds. And then those compounds have a negative influence on the growth of other plants.
And it can be also of the same species.
Sorry?
Can it be of the same species that they?
Yeah, potentially it could be. Yeah.
Young ones of their own species.
Yeah. Okay, so those are 3 mechanisms, and plant density I would not really consider a mechanism that is specific for intercrops, because you could also, of course, also increase the plant density in a pure stand, and then you will also have a better competitiveness. And so an increased plant density is usually associated with an increased plant density. So we also dived into the data that were collected by Chun Feng, and then what I present over here is for replacement designs. So when the density in the intercrop is the same as the density in the two pure stands, then this is the weed biomass, the average weed biomass of the weaker suppressive species, and the more suppressive species clearly had a lower weed biomass. So this was the difference that was found in the intercrops that were laid out in a replacement design. And if you then look at the intercrops, where do you find them? Well, the weed biomass is more or less over here. So very close to the more suppressive weed, crop species. If you do the same for the additive design, then this is what on average was found. Here the weed biomass of the poorly suppressive species, here the weed biomass of the stronger suppressive species. And then what you found is on average that the weed biomass is even lower than the wheat biomass found in the more suppressive species. And this definitely is the influence of an increased plant density. Okay, so, but we wanted to know more. We also wanted to dissect between complementarity and selection, because if we know which one is at play, that will help us to design intercrops that are really weed suppressive. And therefore we made use of the model of Splitters, and the starting point for the model of that Splitters developed is the relation which you commonly find between plant density and the biomass produced by that canopy, which can be depicted by a rectangular hyperbola, which is characterized by two characteristics. So the initial slope is equal to the weight of an individual plant. In this situation, if you increase plant number, the biomass will simply go up in a linear fashion. But as soon as those plants start to compete among each other, they are hindering one another, then it's no longer a linear increase, but it gradually bends off. And in the end, it's not the number of plants that is important, but it's the amount of resources that is available. And then this will result in an asymptote, which we call the maximum yield, and this is the maximum individual plant size. And so those two parameters characterize the shape of this function. And if you want to put this in an equation, you can see that the yield of a crop is equal to the number of crop plants. And then here we find two parameters which relate to this one and to this one. And well, of course, the yield of a crop is composed of the number of crop plants and the weight of individual crop plants, and the product of that will give the yield. And from the above equation, it clearly shows that the individual plant weight, which you find, is equal to this term. And it also contains those two parameters. Now, if you plot this individual plant dry weight against crop plant density, this is what you find. And so initially, if you increase plant number, they will hinder one another very strongly. But the more plants you have, well, whether you have 150 or 151 plants, the size of the individual plant is not so much influenced anymore. Now, the interesting thing here is that if you invert this individual plant dry weight, 1 over W, very strange value because it tells you how many plants you have per gram biomass. So it's a bit weird. But the nice thing about it is that you then get a straight line where this is the intercept and where this is the slope of the curve. So how does that look like? Here we have crop plant density. Here we have this inverse of individual plant dry weight. And it now turns into a straight line with the slope of this line equal to BCC. And this, in fact, was the starting point for the equation of Splitters, because what he noticed is that whenever you add plants now, whenever you add more plants, whether you have 20 plants and you add plant number 21, or whether you add from 100, you move to 101 plants, or from 200, you move to 201, always the increase of a single plant will increase this value with BCC. And so it seems that competition, at least on this scale, simply works in an additive manner. And that observation he used for developing a model that predicts how well plants will grow in a situation in combination with another species. And he said, okay, if they influence one another in an additive manner, then probably also the influence of a second species is also simply a matter of adding those compounds. And in this case, the intraspecific competition is characterized by a competition parameter and the number of crop plants. So the competitive influence of the, in this case, the wheat on the crop is also characterized by a competition parameter multiplied by the number of wheat plants. And that's the basis for this model. And he applied that in an intercropping situation. He applied that in combinations where you have a crop infested with weeds, and usually it gives very reasonable results. So it has been well validated, this model. So how does that look like? Well, if you have a wheat plant, because apart from a crop, you can also apply this to a wheat. If a wheat plant is growing in isolation, it will grow as tall as possible. So it will reach the maximum individual plant dry weight, which is simply the inverse of parameter BW0. Then if you grow wheats in a population stand with only wheats, then intra-specific competition of the wheats on each other have to be accounted for. That means you have to add this intra-specific competition coefficient and the number of wheat plants, and that will give you individual plant weight. Then if you have the same wheat population, but now surrounded by a crop, it means you have to add an additional term which represents the influence of the crop on those wheat plants. So a competition coefficient, an interspecific competition coefficient in this case, multiplied by the number of crop plants. And then you obtain individual size of the wheat plant in that situation.
But is that an individual wheat plants of really that individual wheat, or is it like kind of an average over the population? Because I would say that the distance to the competitors would also matter, right?
Yeah, sure, it matters. So what you are looking at here is wheats and also crop plants growing in a certain density and assuming that they are quite equally distributed. And that is more or less what you assume over here. And of course, if it's not entirely homogeneously distributed, then it still holds. If it's clustered, it's a different story. But the assumption is that they are reasonably distributed. Okay. So in fact, what you can see here, competitive influences, they simply add up. And the intra-specific competition of the wheat on itself, the competitive influence of the crop on the wheat. And well, then if you want to determine the wheat biomass that you found in a certain crop stand, you know that this is the yield of the wheats in that situation, determined by the number of wheat plants. This is this starting point for the wheat if it's growing in absence. This is the competitive influence of wheats on each other. This is the competitive influence of the crop on that wheat. If on the same field you grow a different crop, this part will not be affected, but the competitive influence of the other crop will be different. And so that is what you find. And if we now take this to a situation of an intercrop, well, then we can simply add up the competitive effect of the two crop species. And what we find here is the same pattern as over here. Here we add the competitive effect of the first crop, which is present in a certain density relative to its density in the monostand, and we do the same for the second crop species. And then what you can notice is, okay, those competition parameters present over here, they are the same for all three situations. So it would be nice if we now could determine those competition parameters, because that will give us a better clue on what actually is going on. But based on literature, that's hardly possible, because usually those crops and those intercrops are only grown at a single density. So we simply do not have enough information to try to estimate all of these parameters. So that means, is this a dead end? Well, there might be one solution, and that is what we tried, because perhaps substitution is possible. So perhaps we can express the wheat biomass which we find in the intercrop as a function of the wheat biomass we found in the pure stands of those two crops. And then we did some mathematical giggling. We turned it around. And hey, surprisingly, we found that the wheat biomass you then expect in an intercrop is not the average of the wheat biomasses you find in the two crops, but it's the harmonic mean of the wheat biomasses. So you have to take the inverse of wheat biomass in the two pure stands. You then take the average of this, and then you invert it again. And how does that look like? Well, if in the more suppressive crop we find 4 grams of wheat biomass, in the poorly suppressive crop we find 40 grams per meter square, then the average is simply 22 grams per meter square. If we then use the harmonic mean, and we take 4 and 40, then we can see that the expectation in the intercrop is way lower than this 22 grams per meter square. It's only 7.3 grams per meter square. So it suggests that if you have two crops that are competing both on the weeds, then the influence of the stronger competitive species is way more important. And as a consequence, you get a result that is way lower than what you would expect based on those two if you simply take the average. Okay, so only accounting for competition should result in the harmonic mean of the wheat biomasses you find in the two pure stands. And so it means, in fact, that if we know the wheat biomasses of those two pure stands, we are able to make a prediction of what we can expect in the intercrop. It also means that the wheat biomass is likely to be way closer to the wheat biomass you find in a more suppressive crop. And in fact, this is what is representing the selection effect. The stronger competitive species taking a larger share of the intercrop. And therefore, as a result, the suppressiveness of the intercrop is better than what you would expect. Of course, this is only a theory. And we have this huge database of Chunfeng. And so this is how it looks like. Just a summary of what we did before. Here we put the inverse of wheat biomass again at different total crop plant densities, either in pure stand, the two outer lines, or in the intercrop, and an intercrop composed of exactly 50% of one species and 50% of the other. And what you find is the 1/W is exactly in the middle. If you then express it on individual wheat plant basis, then you get a different situation. Over here, you find the more competitive species. So wheat biomass or the individual wheat plant dry weight rapidly drops because of the strong competition from the stronger competitor. This is what you observe in the weakly competitive crop. Of course, also here, wheat biomass goes down, but at a much lower pace. But in the intercrop, it's not exactly in the middle. No, it's way closer to that of the more suppressive crop. And that is, in fact, this line, in fact, represents the harmonic mean. And so the situation in the intercrop is way better than one would expect. How does it look like in the field? Here we have rye and field pea used in pure stand and in intercrop. If you look at the soil cover at this moment in time, you find that over here, the rye is covering 85% of the soil. At the same moment in time, about 1 month after planting, the field pea only covers 35%. So what one might expect is, because we introduced half of the density of rye in here and half of the density of the pea in here, you might expect 42.5 plus the half of this 17.5 is a cover of 60%. Which actually what we find here is that rye covers a much higher fraction than you would expect based on this. Pea, in fact, covers a much lower fraction than what you would expect based on this. But if you look at the overall cover, it's higher than simply taking the average. So this, in fact, is how selection looks like in the field. And here we have made some schematic representations of this. If this is the weaker competing crop, the crop takes part of the field, it uses the resources, and this is what the weeds will take. And that will result in the wheat biomass in this poorly suppressing crop. If you look at a stronger suppressive crop, then the crop will take a much larger share of all the resources. It will produce more, but still weeds will also take part of the resources that are available in that field, though to a lower extent. Then if you look at what will happen in an intercrop, if you now assume that both crops the intra and interspecific competition among those is not different, then each of them will just move in the same way as they did in the pure stand. And of course, this extends, but for clarification, I only took the lower part of these graphs. And then this is the wheat biomass that develops in the part of the intercrop occupied by the poorly suppressing wheat crop. This is the wheat biomass that develops in the part covered by the stronger competitive crop. And what you find here, of course, is exactly the average of those two. So if here we plot the fraction of the more suppressive species and we plot it against the wheat biomass we find, then this is what you find in one of the pure stands, the poorly competitive one. This is what you find in the stronger competitive one. And what you find in an intercrop entirely depends on the fraction of the more suppressive species, but it's a linear relation. Then if we look into the situation where selection occurs, it means that the crop that is more wheat suppressive, so that has a lower amount of wheat biomass, it will also intrude on the other species, on its companion crop. And as a result, what we find is that also this part is covered. So this is the gain you have due to combining those two crops that have a different wheat suppressiveness. This is the positive effect because this crop takes up a larger share of the intercrop. And if we then take the same function here, those are the wheat biomasses in pure stand, we now can see this is not a straight line, but this is a banded line. And the difference between those two is the gain you have due to selection. Now we can think of another situation that also complementarity is at play, meaning that there is niche differentiation between those crops, and as a result, more resources are taken up, fewer are left for the weeds. Then there will also be a positive effect due to complementarity. And then you would expect that this line is even lower than what we would expect if we only account for selection. Now, what we can do based on the results of Chun-Feng, knowing the pure stand wheat biomass in this crop, knowing the pure stand wheat biomass in this crop, we can of course simply take the average. So this is possible. We can calculate that. We can also use the harmonic mean, and then we will come up with this, and we can see whether what was actually found in the field corresponds to what we expected based on accounting for selection. We cannot do this because we do not know how large the complementarity effect is between two species. But if complementarity would be at play, you can expect that if you make your prediction based on the selection effect, you always overestimate the wheat biomass which you actually find in the field. And that is what we took on in the further study. And so if we find that the observations closely match this straight line, it's just a matter of an arithmetic mean, and the two species are not really interfering strongly. If we find the observations very close to this line, we know that selection is at play. But if the wheat biomasses that we find in the field is even lower than that, we also know that in addition to selection, also complementarity will be important. And that is in fact what we did with the data from Chun-Feng. And here we made a comparison between the arithmetic mean, so the normal average, and the observed wheat biomasses in the field. And you can already see here, if this was the observation, the prediction would be higher than that. So in this case, we overestimate the wheat biomass that was actually found. So the arithmetic mean clearly is not valid. And so it confirms that wheat suppression is better than that. It's simply, in an intercrop, the wheat suppression is simply better than the average of the two species. And well, if we look at the correspondence between this line and what was actually found, we find there is random scatter, which makes sense, but there is also a systematic overestimation of the wheat biomass. So then we did the same, and we used the harmonic mean. And now you can see that in general, on average, there is a very close correspondence between what was observed in the field in intercrop and what was predicted based on the wheat biomass observed in the two individual pure stands. So if we are not making an overestimation of wheat biomass in this case, it suggests, in fact, that complementarity is probably not that important. And it's mainly selection that occurs in the intercrop. And we can make a comparison again, and you can see that all the systematic over or underestimation has disappeared, and only what we keep is a kind of random scatter. Okay, so then we would like to check whether indeed complementarity is not important. So what we did, we also took the land equivalent ratio, and we know that if species really differ and if they have a different niche, then the land equivalent ratio will exceed 1. That's happened here, and then we would expect that the weeds in intercrop are way better suppressed. But actually, when we did that with the data, that's not what we observed. So again, this is an additional proof that complementarity is probably not that important. One might wonder, why is complementarity not important? Because it's a very nice story. You have two species, they take up different resources, and consequently less is left for weeds. It makes sense, right? I believe that this is not the case simply because we are working in annual intercropping systems, so very short growing seasons. So what is very important is how fast the soil is covered by the crops. That is way more important than the competition later on. So early on in the growth stages, the competitive relations between crops and weeds are shaped. And so how fast are you covering the soil is way more important. So a fast canopy closure provides an ability to shade the weeds, and that is really key. Complementarity might play a role, and it might have a positive effect on yielding ability, but for weed suppression, it's not that important. Okay, now just a few more slides to see what we can learn from our understanding. If selection is really the main mechanisms in intercrop, what implications does that have for the design of intercrops? And I think this is a very important one. And we now introduced parameter A, which is the weed biomass in the weaker suppressing crop species over the weed biomass in the stronger suppressing species. So if A is large, it means it's really differ a lot in weed suppressiveness. And that is what is being put on the x-axis here. And this is the relative reduction. If this is the weed biomass in the poorly suppressing species, then this reduction is what is put here. And if you would use the arithmetic mean, this is what is found. So what you can see over here, selection is really at play when crop species differ a lot in weed suppressiveness. So if you want to profit from an improved weed suppression, you have to select crop species that differ a lot in weed suppressiveness. But there is a disadvantage to that, because if those two crops are differing too much, the stronger competitive might easily outcompete the other. So there is a kind of optimum there. But if you only focus on weed suppression, it's evident, and that's also what you can see here, the difference in weed suppressive ability between the two species, that is really what drives selection. So we can also look at the mixing ratio. Does that make a difference, whether we take a 50-50 intercrop or a 40-60 or a 70-30 intercrop? Now, here we calculated the fraction of the more suppressive species that results in the largest difference between the arithmetic mean and the harmonic mean. And so where the selection effect is the strongest. And what you then find, and also here, the difference in weed suppressiveness between the two species is really very important. What you then find is that the larger this difference, the more the optimum ratio moves to the left. That means already a very small contribution of the more weed suppressive crop has a major implication for weed suppressiveness. So if they really differ a lot, you do not have to make use of a 50-50 ratio, but you can do with less. You can perhaps include 25% of the more suppressive species. And then the chances of the stronger suppressive species outcompeting the poorer will be lower. And still, you give in weed suppression somewhat, but not that much. That is what this relation shows. Then finally, spatial arrangement is important. You have been visiting the strip cropping experiment. Now, instead of having a single row of one species alternated with a single row of another species, or instead of mixing those species in the row, you now have strips, so several rows of the crop alternated with several rows of the other. And then, of course, you can imagine that the interaction between the two species is way smaller. And that, for disease suppression or for insects, might be less influential, but for weeds, it definitely makes a difference. Because if we don't have that intimate connection between the two species, then the advantage in terms of weed suppression is soon lost. And so if this is the weed biomass in the weaker suppressive species, if this is the weed biomass in the stronger suppressive crop, so way lower, then this is the arithmetic mean, and this is what we would expect if we are mixing the two species, or if we are putting them in an alternate row design. And so really a substantial effect due to selection. But if we then increase the strip width, and this in fact represents the number of rows within a strip, then we find that from the harmonic mean, gradually this advantage gets lost. And here we are very close already to the arithmetic mean. And that's also what you can imagine. If you have a field and you split it in two, here with crop 1, here with crop 2, then you get, in terms of weed biomass, averaged over the entire field, just the average of this one and that one. And that is what the arithmetic mean represents. So for intercrops to be effective in terms of weed suppression, what we really should aim for is a close interaction between the two species. And that is what this picture shows us. In fact, with 2 rows, just 50% is left. With 4 rows, 25%. And with 8 rows, strip width of 8 rows, just 12.5% is left. So just some items. Selection clearly is the most prominent mechanism responsible for the above average weed suppression of intercrops. And to make use of this, we really need to combine crop species that differ in weed suppressiveness, because otherwise there is no advantage. And close proximity of those species is also very relevant. If the crop species do not differ in weed suppressive ability, but you still want to have an intercrop that suppresses weeds better, the only option you have is to increase plant density. And then due to the additive design, you'll also have a better weed suppression. What we also noticed is that if the two species really differ in weed suppressiveness, then already a very small fraction of the more weed suppressive species already gives quite a benefit. So selection seems very well suited for protection of a weakly suppressive species by a more suppressive species, but care should be taken not to overprotect, because then, okay, the poorer suppressing species is simply hindered by the stronger competitor. And that's where I would like to leave it.
Thank you.